The Taylor tool life equation is a function that we use to represent the inverse trade-off between the log of the cutting speed and the tool life. So if we look at the form of the Taylor tool life equation, it takes a V, which is the cutting speed in either feet per minute or meters per minute, times T, which is the tool life in minutes, to the N power, which is the Taylor tool life exponent. And that's going to equal a constant, V1. Many resources call it C, but in here we're going to call it V1 so that we can remember that it carries the units of cutting speed. You see in the middle left a plot of the cutting speed versus tool life on a regular linear plot. It's difficult to do mathematics with that plot though, because it's on a linear scale and the functionality is not linear. So the approach beginning a long time ago was to plot on log paper the cutting speed versus the tool life. And this is easier if we put the tool life on the horizontal axis because of the form of this equation. If you take the log of both sides of the Vt to the n equals V1, you get log of V equals negative n log T plus log V1. And you can apply that directly to the y equals mx plus b linear equation, where m is the slope, so that's rise over run. In this case, it's negative, and therefore our n value, Taylor tool life exponent, n equals negative m, so that we can keep n a positive value. It's going to be very helpful for you to remember that n equals v rise over t run. That way, if you remember that n equals v rise over t run, even if axes are inverted, like you see in the upper right, log t is on the vertical axis and log v is on the horizontal axis, you remember that n equals v rise over t run. Each different material that you use as the cutting tool material on each different material that you actually cut on or turn on is going to have a different trend. And so we see a plot here for the Taylor tool life exponent in range and the V1 constant range for different materials being used to cut ductile cast iron. Now in this plot, grid marks have been added to show the decades. You see there the bottom of the plot starts with a tool life of 1 minute, and then it goes up to 10 minutes, and then it goes up to 100. So that's 2 decades, and the top of the plot is at 300, so that would be another half decade. On a log plot, 300 is about halfway between 100 and 1000. And so if you want to get that T run over V rise to approximate the tool life exponent n as closely as possible, you could use this small triangle, but it's going to be easier to expand that triangle based on similar triangles and to get as much of the useful part of that curve within your field of view as you can to identify the rise and the run. So here I've expanded that triangle. You see the T run then is about 2 decades and the V rise is about 1.5 decades. And so since n is V rise over T run, it's 1.5 over 2, and that's 0.75. And you can see from the table that 0.75 is about halfway. It's in about the middle of the range of using ceramic tools to cut ductile cast iron. The range in the table there is 0.5 to 1. So here's an example. This is a plot where now we have the tool life on the horizontal axis and the cutting speed on the vertical axis, and we have a lot of different materials that are used to cut both as cast and as extruded aluminum matrix silicon carbide composite. The material we're cutting doesn't matter. You don't have to know what that material is. We are looking at using our understanding of the Taylor tool life equation in this example. And here's our question. Identify the V1 and the exponent n for Vt to the n equals V1 for machining the aluminum matrix silicon carbide, the extruded version of it, using a tungsten carbide tool for the plot below, and then estimate the tool life for a cutting speed of 1 meter per minute. The first thing I need to do is find the trend that I'm looking for. There's the tungsten carbide. I relabeled my axes just to clarify which one is the V and which one is the T. And our solution is going to start with finding that V1 value. V1 value is for a tool life of 1 minute, which is 10 to the 0 power, go from the horizontal axis up to the WC line, so the trend that we're looking for, and then go left to the vertical axis and find what value that intercept is at. And I'm going to put a little ruler on there so I can take a closer look. I can see when I look at that ruler that it's somewhere around 22. So the solution, V1 is the intercept at 10 to the 0 power, which is 1 minute, which occurs at about 22 meters per minute. So now we need to identify N. N is the V rise over T run again. V rise over T run. In this case, V is the actual vertical axis and T is the actual horizontal axis. So V rise is about 2.3 decades. And T run looks to be about 3 decades. So V rise over T run equals 2.3 over 3, which is about 0.77. And so VT to the N equals V1. If we plug in the constants that we just calculated, we get VT to the 0.77 equals 22. The next part is to estimate the tool life. We rearrange to solve for T. So T to the 0.77 equals 22 over V. And then we have to take the log of both sides like so. And then we get T by itself. And so we have to undo the log, we take 10 we put that quantity in our exponent of the 10, plug in the V of, what were we looking for? 1 meter per minute. Plug in that V of 1 meter per minute. So the log of 1 is going to be 0. We get log of 22 over 0.77. We're going to get 55.3 minutes. And these are approximate. You can see from the nature of these calculations that they are only good to about plus or minus 10%. So here's one example of the same type of problem for you to try on your own. The solutions are here as well. Go for it. Good luck.